Start recording.
Sir, recording started.
Okay, thank you, Shubham. So, coming back to the simple derivation we have done yesterday regarding shearing of the two planes along with their top and bottom part upon the application of a shear stress. And we have shown that there would be a between two atom positions, there would be an activation barrier, something like this. And that barrier needs to be crossed. And for that, you need to calculate how much force or stress you need to apply. So that you get from the slope of that activation barrier plot, from the potential energy distance plot. The slope of that is here, and that slope is basically the force. If you divided it by area, it will give you the stress. So directly we are talking about the shear stress here, because shear stress causes plastic deformation. Shear stress causes plastic deformation. So we have considered that you have to push the atom to a saddle point. This is called the saddle point. That is a sufficient distance x where you just cross elastic regime, and as you cross that elastic regime with sufficient stress, you make sure the atom will move into the next equilibrium position. And by this process, you will find a extra atom will situate somewhere in between and a dislocation will be created. So what we are talking about is the creation of a dislocation by the application of shear stress. By the application of shear stress tau, how much stress is needed to create a dislocation. And the final derivation we have come to, maximum stress required is G by 2 pi B by A, where G is the shear modulus, B is the interatomic distance between two neighboring atoms on a plane, and A is the interplanar spacing of the slip planes. So these are for the slip planes. Since B and A are of the same order, so we can take this term nearly close to 1. So ultimately we see that G by 2 pi term governs the stress requirement, and G is the shear modulus. So higher the shear modulus, more shear stress need to be applied to create a dislocation. This is our conclusion. Now G, typically we said for iron, say 80 GPa, and we have divided it by 2 pi. So we have come down to a value of 13 GPa. So to create a dislocation in iron and cause plastic deformation, you need 13 GPa strength. But we also have said that typical strength of iron starts from 200 MPa. Or if you take pure iron, Armco iron, it may be even less. And maximum strength goes up to 2 GPa, not more than that. And typically, if you see the structural steels that are used, which contains carbon, which gives additional strengthening compared to iron, there the yield strength typical value is 300 to 500, 600 MPa. Above 600 MPa, it is considered to be high strength. But to cause plastic deformation, you need a stress of 13 GPa as per this derivation. And then I asked, what causes this discrepancy? Why at a much lower stress value yielding takes place? And by now you know that yielding is small but detectable amount of plastic deformation, where as many as 10 to the power 5 to 10 to the power 6 number of dislocations move. So what causes this discrepancy? That is my question. So what is your answer? I want to know.
Sir, 300 to 500 MPa is the amount of stress required to move a dislocation, and 13 GPa
Right.
is the amount of stress required to produce a dislocation.
That's right. That's the right answer. So what we are talking about is, through this derivation, the tau m value tells us that stress required to create a dislocation inside what?
Material.
No, more specifically you have to say material is understandable.
Perfect crystal.
Perfect crystal, that is the right answer. Perfect single crystal. If I give you a perfect single crystal without any defect, all the atoms are at their particular position without the presence of any dislocation, all atoms are at their perfect position and the structure do not contain any initial dislocation. So there your challenge is, to cause plastic deformation, you first have to create a dislocation and then move the dislocation. Then the step will form. So creation of the dislocation is the challenge. That requires 13 GPa. So I asked that when will you find in pure iron also deforming at 13 GPa strength? Is it possible that a pure iron deforms at 13 GPa strength? Starts the deformation at 13 GPa strength? What is your answer?
In nanobias, it can be possible.
Answer is
No,
you have to produce a single crystal which is perfect. If you can produce a single crystal which is perfect, perfect means no dislocation is there from beginning. If you can do such thing, if you can produce such a single crystal, you will find 13 GPa strength will be required to plastic deformation start. Just the onset of deformation will require 13 GPa. But what happens when reality, when we produce a metal,
It has defects.
yes, yes, defects are inherent. Very right, very good answer, very appropriate wording. Defects are inherent. Like human being, always there is some defect or some other. So that is the nature, that when you produce, either you produce by casting or you produce by powder metallurgy route, whatever, you will find some you see big defects, pores, cavities. So those are there, means dislocation is must be there. Incomplete planes and things will be there because there will be associated material shrinkage, solidification. So that process itself generates good amount of strain and defects form. So already there is defect inside a macroscopic material. When a material will have more defect in it, this is my question. When suppose a metal contains more defect, This is my question. No answer.
Cold work material.
Huh?
Cold
Yes.
worked material.
Okay. You are right. The answer I was looking for is, even the casting quality is not good, then also it will contain a lot of defect. My answer is when it is big, when it is large. So anything large you produce, naturally more defect will come inside it. If you can produce something very small, then always defect will be less. So that is actually your challenge. It's easy to develop a single crystal defect free or less defect, but it's not possible to create a defect free bridge made of metal, because when you make something big, more and more defect will come inside it. So that is the challenge of structural materials research, that here you have to deal with big things, and big things are more defected. So they can deform easily, they can fracture easily. Compared to that, if you make something very small, then defect density would be less. So if I ask you, when we want there will be no dislocation, in application, do we need something where we do not want any dislocation to be there?
No, sir. It also affects the mechanical properties.
In something, some application, can you tell where we do not want
Yes, sir.
dislocation? Yes, tell. Where?
Creep, sir. Creep resistant. Creep resistant materials.
So semiconductors.
Yes, the second answer is right. Creep resistant material
Sir,
is
in
again
creep-
a structure. In large volume of material, there will always be some defects, but completely dislocation free crystals we try to make for electronic applications, right? Your computer chips and all those things. Because if there is a dislocation, it will hamper, if there is defect, it will hamper the flow of electrons. So there we want absolutely dislocation free, vacancy free, perfect single crystals. Okay, so there we use crystal growth. You cannot make something completely defect free by these routes, general processing routes. You have to do crystal growth, where we go for layer by layer atom deposition. You deposit one layer, and then you deposit another layer, then deposit another layer by very careful way of atom deposition. There are certain methods by which you can produce defect free single crystal, which is called whiskers. So there you do not find any defect, and if you want to create defect, you may need very high stress. But in general, in structural materials, always it contains defects in the form of vacancies and dislocations. And when you apply stress, you need not have to create a dislocation. This is what I showed, is this atom coming here because of the creation of a dislocation. Already there will be something like this. So there you need to apply stress sufficiently high so that this dislocation can move. And as the dislocation moves, a step will be produced here. That's why at a much lower applied stress, you see your yielding takes place. So this concept is very important. Coming to one more very important concept. Here we are plotting a single crystal. This is a single crystal. But it is not defect-free single crystal. There is one dislocation or other defects can also be there. But the concept is applicable to single crystal. And predominantly those single crystal where there is a predominant slip system. There is a one dominant slip system. Sometimes we find systems like BCC where multiple slip systems are there. But here we are considering one slip plane and one slip direction. So it's predominantly for, let us consider for FCC single crystal. So this is the crystal I have drawn. This is the crystal I have drawn. You can see. I am applying a load P. Applying a load P. Let us take this side is hinged. So an equal and opposite reaction is acting this side also. Now, we have to consider how the slip will occur. So how the slip will occur and how the shape will change, what factor does it depend on? What will decide how the shape change will be?
All shear stress.
You have to consider how your slip plane is. Okay. So A0 is the area of cross-sectional plane. I have drawn this black plane as cross-sectional plane. It's showing the cross-section area of the cylindrical crystal. And its area I am writing as A0. Cross-sectional area A0. And in blue color, I am writing another plane with area A. Area of that particular plane is A. This blue color inclined plane. Blue color inclined plane here. So this inclined plane is my slip plane. This inclined plane is my slip plane. And in red color, I have drawn on the slip plane, I have shown a direction. So this direction D is lying on the slip plane. This direction D is lying on that plane having area A. So this is my slip direction. So what decides which plane will be the slip plane and which direction will be the slip direction? What decides that?
So lower axis.
What decides? What differentiates one plane to other? What decides? Yes.
Schmidt factor.
Say inside a FCC, there are many planes. So which plane we call shear plane, slip plane?
Critical resolve. Lower shear system.
Closed back
So-
plane.
So which plane is the closed crack plane? In
FCCs
FCC,
are 111.
111. So which factor decides that dislocation movement will be easier on 111?
The Schmidt factor decides.
It's wrong.
Planar density, sir.
Is bomb strength.
Critical resolve.
Absolutely not right. So that is the problem actually happening. You are not learning. Huh? Who said? What is your name? Ashish. Pearl stress. We have talked about Pearl stress, na? Pearl stress. Pearl stress tells that dislocation movement will be easy on slip plane along slip direction. Because if the slip direction, if B is small and A is large, then we have seen the Pearl stress is less. So lattice friction will be less. So it will be easy to move a dislocation. So that identifies slip plane and slip direction. Now whether slip will occur on the slip plane or not, that is decided by critical resolve shear stress, mid factor, whatever you are talking about. So this plane A and D are identified at slip plane and slip direction because of their combination gives the minimum Pearl stress value. That's why we call the plane a slip plane. That's why we call a direction slip direction. Now here in this case, it's favorably inclined. So we are trying to calculate how much stress is required to cause slip. So first we have to calculate the resolved shear stress. Resolved shear stress, RSS. What is RSS? What is the component of applied load P acting along the slip direction D? That we have to consider. So that is actually the shear stress along the slip direction on the slip plane that we call resolved shear stress. That is the resolved component of applied stress. So what would be that value? What would be that value?
P cos lambda.
What would be the area of that plane? So P cos lambda is basically force, right? Resolved component of the force. It is not stress, it is force. P is force. So P cos lambda is the force acting along the slip direction on the slip plane, shear force. So how much would be the stress? We have to divide it by what?
Area.
We have to divide it by area. So how much is the area A? If we represent area A in terms of A naught, because A naught is the cross-sectional area, it is easy to measure. Sorry. A naught by cos phi. So here you write A naught by cos phi. What is n here? Because the direction n is making an angle phi with P, with the direction of loading, which is also the longitudinal direction, which P is also the longitudinal direction of the crystal. P is applied along the longitudinal direction of the crystal, which is perpendicular to the area A naught. What is n?
Sir, n is perpendicular to A.
N is the slip plane normal. It is called slip plane normal. A is the slip plane normal to that, normal direction to that plane. It's very important, slip plane normal. Okay, so the value that we get ultimately is P by A naught cos phi cos lambda. P by A naught cos phi cos lambda. Very simple way it is derived. And that is the resolved shear stress. That is the resolved shear stress acting along the slip direction on the slip plane. So according to the concept, when slip will occur? When slip will occur?
When resolved
When
shear
the
stress is
shear
equal to
stress reaches
CRSS.
the
When resolved shear stress exceeds a critical value. Critical. That's why now the critical will come, C. So CRSS, you have to break it down. First, you have to understand what is a resolved shear stress. And it needs to exceed a critical value. So you need to put a symbol this here. So when the resolved shear stress equals or exceeds a critical value, then slip will occur. So that is called critical resolved shear stress. And that critical value depends on crystal system and all other factors. Whatever factors control your strengthening, this critical value depends on that. So as I said before, that ultimately the dislocation motion is the movement of a car on the road. So Paul stress considered, there is a single car and you are driving the car on a highway and there is no other car or nothing, no barrier is there. So that decides the condition of the road. If the road is smooth, your journey will be comfortable and easy, fuel efficient. But if the road is uneven, then even if no other obstacle is there, your journey will be uncomfortable. So that decides the Pearl stress, how the smoothness of the plane is, how good is the road. But critical resolved shear stress considers first the orientation of the slip plane and slip direction with respect to your loading direction. This first factor, it considers its orientation. For example, to drive a car, you need to move along the road. If someone goes down the car and try to lift it up, will it make a journey? Suppose you go down the car and Palwan lifting it up. Will it move distance? No, because that loading is of no use. You will move towards sky, but you will not have your journey. So that is unfavorable loading. Suppose my A0 plane was the slip plane. If I load along P, would the slip would occur or not? if my A naught plane was the slip plane?
No, sir.
Because cos lambda would be cos 90 degree. So straight away the resolved force is 0. Similarly, I am drawing another plane. Very sorry. I am drawing a plane which is the perpendicular plane. I am drawing a perpendicular plane. On that plane also, there will be no shear stress, because basically you are stretching the atoms in that plane. Whatever atoms are there, you are basically stretching those atoms. You are not pulling, you are not shearing, but stretching. And as a result, the plane normal is 90 degree with respect to your loading. So phi is 90 degree. So cos 90 degree will again be 0. So this plane or that plane, in both cases, there will not be any slip. If the slip planes are oriented in this way, no slip. So what would be the most favorable condition? According to this theory, what is the most favorable condition?
45 degrees, sir.
45 degree. Very important. 45. Very important. 45 degree. And it is considered that if you apply stress, maximum resolved shear stress in a body, maximum shear stress will be 45 degree with respect to the principal stress. Later on we will learn what is principal stress. Here the P by A naught is my principal stress, because it is acting on the plane A naught where there is no shear stress. So principal stress is called principal stress because it acts on a plane where there is no shear stress. So P by A naught, this stress is basically my principal stress, and that makes my principal direction. This is principal direction. And if you can take 45 degree, both phi 45 degree, lambda 45 degree, that is the best condition. Because 1 by root 2, 1 by root 2, that value will be half. So cos phi cos lambda, what it decides? Cos phi cos lambda. What is that called? Schmidt factor.
Orientation.
Right, very good. Right. Schmidt factor, which is the orientation factor. How the slip plane and slip direction is oriented with respect to your loading direction. With respect to your loading direction. A naught plane will not be slip.
Sir?
If my loading is along P, yes, I'm taking your question. But if I have suppose load in another way, if I applied P in this way, then this A naught plane slipping would be possible because there will be resolved shear stress on this plane. And if it exceeds criticality, then slip would occur. So you have to increase P so that a sufficient value is reached so that this condition is satisfied. So how your slip plane is oriented with respect to your loading direction, that is most important. Yes, please ask your question.
Sir, can you please repeat it once more?
Which one? Which part?
So this cos phi and cos lambda, Schmidt factor basically.
Schmidt factor, yes, yes, yes. First of all, your applied load is along the direction of P. and the amount of load is P. Okay. So the load, applied load is P. And this blue plane, blue colored plane is your slip plane. And this red colored direction D is your slip direction. So first you need to know that how much would be the shear force acting on that particular plane along that particular direction D. How much would be the shear force? It must be component of P. Sorry, in this direction. So how much would be the shear force? We have to consider the angle between the applied load and the direction. So that is lambda. So it is P cos lambda. P cos lambda is the resolved force. I want to calculate stress. So I have to divide by the area, because stress is force by area. So area of this plane, what is the area of this plane? Area of this plane is A naught by cos phi, where phi is the angle between that plane normal N and longitudinal direction of the crystal where load is acting, P is acting. So that angle is phi. So that area is A naught by cos phi. The area A, slip plane area, is A naught by cos phi. So what would be the resolved shear stress? P cos lambda by A naught by cos phi. So ultimately what would be this value? P by A cos phi cos lambda. And that is called resolved shear stress. And when the slip will occur according to this theory, when the resolved shear stress exceeds a critical value. Equal is the critical condition, exceed is satisfied condition. If it exceeds the critical value, some MPa value, then slip will occur. And as I said, that this concept considers all barrier. In the road that you are traveling, actually, it seldom happens that you are having a sole lone journey. Always there will be obstacles. There will be pedestrians, there will be other vehicles, there will be trucks, buses, tempo, mini trucks. So those are basically your barriers. You need to overcome them. So those barriers are your strengthening mechanisms. There can be dislocation. There can be solute atom of other solute atom. There can be precipitate. So these are the obstacles to your road. So you need to overcome all these obstacles to exceed this criticality, to reach that condition so that slip can occur. So ultimately this cos phi cos lambda value actually decides, because we will have a certain P, you have a certain cross-sectional area. This is more or less fixed if you apply a certain load. But what will be the resolved shear stress? That will be decided by cos phi cos lambda. And if you have 45 degree, then your resolved shear stress is maximum. If your plane and if your direction is at 45 degree. If your phi and lambda both are 45 degree, then that is the best condition. Why I am showing this direction? Can you tell why I am showing this particular angle xi? I have not told so far. Could you understand why I am showing this particular direction? I'm showing this particular direction and this angle. Why? Can anyone figure out? I am showing that direction to make you understand that plane normal N, loading direction P, and slip direction D need not be on the same plane. Okay, one is something like this, one is something like this, one is something like this, and you don't think that these fall in the same vertical plane. Need not be. Okay, that's why I have shown this direction in blue color, because phi plus xi equal to 90 degree. Don't think phi and lambda equal to 90 degree. Phi plus xi makes 90 degree. Okay, so you visualize this D can be like this also. This D can be like this also. Whatever your direction, slip direction be. So don't take it that direction N, plane normal, loading direction P, and slip direction lie on the same vertical plane. They need not lie on the same vertical plane. You could understand. So the way D is in that direction will slip occur. Say slip can occur something like this. Or slip can occur something like this. Depending on the direction, this direction on this plane can be this, this direction on this plane can be this. So accordingly your slip will occur. Don't consider that phi plus lambda equal to 90 degree. Because phi is the angle between N and P, and lambda is the angle between P and D. When a single crystal deforms, what happens? You consider this as resolved shear stress. You consider x-axis as shear strain gamma. It actually looks like this. If you draw the stress strain curve of a single crystal, and not defect free single crystal, a single crystal that contains a dislocation. In critical resolved stress concept, we consider how much stress you need to move one dislocation. If there is no other dislocation, its value will be less. If more dislocation, its value will be more in the starting condition. Suppose you have only one dislocation. How your stress strain curve would look like? It comprises of 3 stages. This is stage 1, this is stage 2, and this is stage 3. In stage 1, you will find as you cross the critical resolved shear stress, suppose there was no other dislocation was there and only one dislocation was there initially. As you cross, initial deformation would be easy. So you cross that particular barrier, you will get sufficient amount of strain. Then as a dislocation moves, as deformation occurs, from one dislocation, more dislocations generate. This is called multiplication. This is called dislocation multiplication. Like a virus, when it goes inside the body, it produces millions of replicas. So more and more dislocation will start forming and moving and more deformation. That is why you are getting more permanent deformation strain. So eventually you will find that lot of dislocations are there and they will now start interacting with each other. So you will find your stress requirement is significantly increasing. So that is called strain hardening. Because of strain, it got hardened because a lot of dislocations are produced. And eventually, when the number will be very high, then so much stress will be generated. The stress will now be very high to cause further deformation. So at that point, what will happen? That some of the dislocations will now move into other plane or recover. So it comprises of 3 stages. First stage, what the first stage is called? When the dislocation movement is easy, it's called easy glide. Easy glide. Please write down easy glide. Can one of you repeat what I have said? Can one of you repeat?
Easy glide.
Easy glide. Can one of you repeat what I said?
Easy glide.
Easy glide. Then I am using another word. Write down linear hardening. Linear hardening. Hardening in a linear way. That means the hardening rate is very high. Can someone repeat what I said?
Linear hardening.
You please again repeat what I said.
Linear hardening.
Then a stage will come when stress becomes so high that cross slip occurs. Cross slip leads to dynamic recovery. Cross slip leads to dynamic recovery. That means now dislocations will rearrange and relatively come to a stable configuration, annihilate, rearrange, and stable configuration, so that subsequently again you will find the rate of hardening decreasing. Here the rate of hardening is lower. Here the rate of hardening is very high. Here the rate of hardening was low, very low. That's why easy glide, linear hardening, and what is this called? It is called dynamic recovery. Dynamic recovery. Can one of you repeat what I said?
Dynamic recovery.
Now you tell 1, 2, 3 together. Three term.
Easy glide, linear hardening, and dynamic recovery.
Again you repeat.
Easy glide, linear hardening, and dynamic recovery.
Very good. Very good. In a single crystal, remember this plot is applicable to a single crystal. So the story is something like, if a football player is there, you give him a football, him or her a football, and ask the player to score a goal. So it will be a very easy process. Goal scoring would be very easy. Now seeing that player playing, 5 more has come. Some of them are defender, some of them are midfielder. So now for striker, the goal scoring is not so easy. Now seeing that 11, 22 players have come into the pitch, then real challenge, World Cup football, linear hardening, difficult to score a goal. Then seeing them, all the spectators got excited and jump on the pitch. So now 1,000 player, tremendous situation, maramari going on. So now police will come and give a charge. Whoever is able to fly in whatever way, they are flying out. So that is dynamic recovery. The question with which I am leaving the class is, when we see tensile testing, we don't see this kind of a behavior. Rather, we find, so here elastic region I have not shown, okay? Elastic region is there. This is the elastic region. You consider a very small elastic part is there. It is almost ignored. So again, I can ignore the elastic part, where polycrystal also show something like here. How the polycrystal curves look like in a tensile specimen, how the stress strain curve look like? Do the plastic deformation region look like this?
No, sir.
No. How do they look like? Something like this, right? Something like this. And then eventually, if it is a engineering stress strain, it will come down. If it is true stress strain, it will go like this. So what is the difference between a single crystal stress strain curve and a polycrystal stress strain curve? And polycrystal stress requirement, you will find, is higher than the single crystal. You will not find during tensile stress yielding occurs at resolved shear stress. Critical resolved shear stress values are lower. In polycrystal, you will find yield strength are much higher than the critical resolved shear stress values. So you have to understand the deformation of single crystal and deformation of polycrystal. There is some similarity and some dissimilarity. And actually polycrystal curve will be above the single crystal curve. Okay. So tomorrow's class, you please try to give me the answer. I am done for today.
Thank you, sir.
Thank you.
Thank you, sir.